First, I want to thank the organizers and everyone involved in this meeting. It's been really great to be here and to listen to some really excellent talks. So thank you to all the speakers and the organizers. I've really enjoyed it. For those of you who I don't know yet, my name is Stephanie Waterman. I'm a physical oceanographer. I'm usually at the University of British Columbia in Vancouver, Canada, spending the year at Oxford University in the UK this year, which let me come to this meeting. I've had a long-standing interest in eddy-mean flow interactions, and I like to play with very, very idealized models to try to understand them. In the last couple of years, I've had the pleasure of being a supervisor of Connor Henderson, who was a master's student at UBC with me. And he picked up some of the ideas that we had been working on several years ago about eddy geometry and made some forward progress with them. And that's the work I'm going to talk about today, and I hope to do it justice. Okay, so now it's not working. Okay, great. So I don't need to do the big picture context for most of the people in this room, but I think it's important nevertheless to give the very big picture context. So eddy effects at all scales need to be better understood and included in our description and our understanding of the larger scale flow dynamics. And the important effects that are not fully resolved by numerical simulations, of course, should be parameterized. And even with all the really amazing, really high ultra resolution modeling, and some of which we've seen today at this meeting, I think this will remain the case in many applications for the foreseeable future. And a lot of the contemporary efforts, as many of you, of course, know, in eddy parameterizations is to think about parameterizations that are flow aware, so reacting to the flow conditions, that are scale aware, so scale with the resolution, and that are energetically consistent. So one of the eddy parameterizations that I like very much is the geometric parameterization. Hands up if you've heard of the geometric parameterization. Okay, all right. Okay, so that stands for geometry and energetics of ocean mesoscale eddies and their rectified impact on climate. It's a framework for parameterizing eddy-mean flow interactions that was first proposed by Marshall and al. In 2012. And the geometric framework parameterizes eddy effects in terms of the dimensional eddy energy, and then 5 non-dimensional parameters. I'm going to call those the geometric parameters for this talk, which describe the eddy stress tensor structure. And I'll say a bit more about that later. In this way, this parameterization respects eddy energy constraints. And then I also like it very much because these geometric parameters, these 5 non-dimensional parameters, have direct connections to the eddy horizontal momentum fluxes and the eddy buoyancy fluxes, or the form stresses. They have direct connections to classical instability theory, and as such, they connect to physically intuitive descriptions of eddy-mean flow interaction. So that's why I like it. To implement geometric as a framework, we need the eddy energy. So we could maybe run an offline model to understand how the eddy energy is evolving. But then we also need to specify these geometric parameters in some form. And so we need a framework in which to do that. And there has been some nice work in recent years making progress to developing a theoretical framework for this specification in barotropic and baroclinic and in a mixed instability system. So this work has been started. But I think it's fair to say that a systematic understanding of how these geometric parameters describe and differentiate systems with different flavors of eddy-mean flow interaction is still needed. And I think this understanding is very useful because it would allow us to better understand how we should prescribe these geometric parameters if we were going to implement this as an eddy parameterization. And I think also it would demonstrate or let us understand the utility of this framework as a tool for understanding eddy-mean flow interactions. So not for parameterizations, but actually as a diagnostic framework for me to understand what's going on in observed or modeled flows. Okay. All right, so that brings me to what this study is about. And in this study, we use an idealized jet model to try to understand how these geometric parameters relate to eddy-mean flow interaction dynamics. And specifically, we're going to perform a set of model runs in which, in a jet model, in which we prescribe the jet parameters such that we're varying the relative importance of barotropic to baroclinic instability in this jet system systematically. And then what we're going to do is we're going to diagnose the geometric parameters in this set of runs and try to understand how the variability in the geometric parameters describe this transition from barotropic dominated to baroclinic dominated dynamics. Okay, so for the remainder of my talk, I'm going to tell you a little bit about the experiment design. I'll briefly talk about the model setup and how we design this parameter study. I'm then going to give you a 2-slide crash course on the geometric parameters and what they represent for those of you who aren't intimately familiar. I'm going to give you results in the form of 4 take-home messages, and then I will summarize and talk about next steps. Okay, so this is our model setup. So we are using an unstable jet model. The model is 3-layer, quasi-geostrophic. It's on a mid-latitude beta plane. Our model is forced at the western boundary here by a jet inflow. And so we prescribe an inflowing jet profile at x = 0 in each of our 3 layers. We let this jet evolve freely in x or downstream. And in this way, it's attempting to model the dynamics of an inertial, unstable jet, like a western boundary current jet extension, the Gulf Stream or the Kerr Sheet, for example. We have to take the jet out at the downstream end of our domain. We do that in a way that we hope is insensitive to the upstream dynamics. We have sponge layers on all our lateral boundaries to model open ocean conditions. And yes, as I mentioned, this is supposed to be an idealized model of a western boundary current jet extension. This is a very similar model to ones that we've used in work previously. Connor's updated this model to make it 3 layers so that we can play more with the baroclinic structure. Okay, so how do we design this experiment? So what we want to do is vary the relative degree of barotropic and baroclinic instability. And we do this by varying the inflowing jet profile at x = 0. We do this specifically by varying the relative importance of horizontal to vertical shear in setting the meridional potential vorticity gradient of this jet, and hence its linear stability properties. So specifically, Connor set up a run. Run 1 has a very strong narrow jet in all 3 layers, so it has lots of horizontal shear and is subject to a heuristic necessary condition for barotropic instability. And then for subsequent runs, he systematically decreases the jet strength in the lower layers, thus increasing the vertical shear and increasing the amount at which the vertical shear is contributing to the PV gradient variation. Okay, any questions? All clear. Great, thanks for the nods. Okay. All right, and so we define a metric to quantify the degree of barotropic instability and the degree of baroclinic instability related to this inflowing jet profile, specifically properties of its meridional PV gradient. And based on these definitions, we have this set of 16 runs that systematically are going from strong barotropic instability to weak barotropic instability. At the same time, we're going from weak baroclinic instability to strong baroclinic instability. Okay. All right, so the eddy-mean flow interactions in this set of runs are very interesting, and if I had lots of time, I would tell you more about them. This is just kind of to give you an illustration of the range of eddy-mean flow interactions that we're accessing. These are bulk measures, so I'm taking, or Connor's taking, the average of this metric in the upstream region, upstream of the eddy kinetic energy maximum, and characterizing each run. And I won't talk about the details, but what you see is that there's variation in these parameters, but they're not always monotonic. And this is illustrating, even though we kind of systematically varied our inflowing conditions, some of these parameters, because of the interaction between the barotropic and the baroclinic instability, are not varying monotonically. And that might be important to keep in mind when we're interpreting the geometric parameters in a minute. Okay, so a crash course on the geometric parameters for those of you who aren't familiar. The geometric framework is exploiting a description of the eddy stress tensor, or the EP flux tensor, a description of its eigenvalues and its eigenvectors. And so you can visualize the eigenvectors and the eigenvalues of a system via an ellipse or an ellipsoid. So for a 3x3 matrix, that visualization is a 3-dimensional ellipsoid. It can be helpful to abstract this geometry into, like, to project it into 2 planes, into like a U' V' plane and a B' U' plane. And so then if you do this projection, now you can describe the geometry of two-dimensional ellipses, all right? The horizontal cross-section has direct connections to the horizontal eddy momentum fluxes, and the vertical cross-section has direct connections to the eddy buoyancy fluxes or the eddy form stresses, okay? All right, so then at the end of the day, you have 5 non-dimensional geometric parameters to describe this ellipsoid geometry. You have 2 ellipse anisotropies that are related to the anisotropy of the horizontal momentum fluxes and the buoyancy fluxes, respectively. You have 2 orientations or ellipse tilts, and they have to do with the direction along which these anisotropic fluxes are oriented. And then you have 1 more angle left, which has to do with the vertical orientation of this ellipsoid in the U prime, B prime space. And so that vertical orientation is actually a function of the ratio of eddy kinetic energy to eddy potential energy, okay? I'm going to refer to these parameters as the Reynolds stress ellipse anisotropy and tilt, the form stress ellipse anisotropy and tilt, and then this vertical angle I'm going to call the eddy energy partition angle, or lambda, okay? All right, so there's 4 key results that I want to show you today, and they're as follows. First, that the geometric parameter magnitude can vary across the runs in systematic ways. Second, that there can be lots of interesting systematic patterns in space in a single run of these geometric parameters, and these patterns can be distinct depending on the dominant instability mechanism. I'm going to try to connect these spatial patterns and geometric parameters to spatial patterns in eddy-mean flow interaction metrics. Again, these relationships will depend on the dominant instability mechanism. And then in a bulk sense, the geometric parameter magnitude can vary systematically with metrics of eddy-mean flow interaction, but some parameters, and specifically the ellipse anisotropies, seem relatively insensitive, and we thought that that was kind of interesting and maybe surprising. So just to show you some examples of the results that support these statements. So key result 1 is that geometric parameters, the magnitude of them can vary across runs in systematic ways. So here I'm showing, it's a fancy pointer. Let's see if I can make it work. Oh, it's very hard. I'm going to use my finger. I'm sorry. This is the Reynolds stress ellipse tilt, the form stress ellipse tilt, the eddy energy partition angle, all right, as a function of run number. So this is the barotropically dominated run. This is the baroclinically dominated run. And so we're just looking at bulk magnitudes. Again, this is the average inside the jet in the upstream region, upstream of the eddy kinetic energy maximum. And this is the variation that you see. And you don't have time to look at these carefully, so I'm going to just point some things out to you. The Reynolds stress ellipse tilt decreases kind of systematically as the degree of the barotropic instability decreases. That makes sense. The form stress ellipse is positive for barotropic dominant cases, and it's negative for baroclinic dominated and mixed cases. That also makes sense. That's the sign of the eddy form stresses. And then the eddy energy partition angle also shows some systematic variations. It's smaller for the barotropic dominant cases and larger for the baroclinic dominated cases. So there's some nice systematic patterns in the angles, in the tilts. All right, I'm going to, for the sake of time, skip those details and move on. But the anisotropies show less systematic patterns. So this is the same view, but for the bulk average anisotropies for the Reynolds stress ellipse and the form stress ellipse is a function of run number. All right, and we see that there is non-monotonic variations with inflowing jet stability characteristics in both of these fields. And the range of variability in these average anisotropies is relatively small, okay? So that's interesting. It's also maybe interesting that the form stress ellipse anisotropy on average tends to be higher than the Reynolds stress anisotropy in these runs, which suggests that the eddy form stresses are more efficient than the Reynolds stresses in this setup. So that's kind of interesting too. All right. Key result number 2 is that there are systematic spatial patterns. 5 minutes. Yeah, sure. Thank you. And again, that these patterns can vary depending on the instability mechanism. Again, there's a lot to see here. What I'm showing, all right, is the cross-jet structure, all right, of the parameter as a function of run number and color. The long jet evolution inside the jet of the parameter as a function of run number, and the cross-jet structure in the downstream region and the upstream region as a function of run number. Okay, and these are the three angles: the Reynolds stress ellipse tilt, the form stress ellipse tilt, and the eddy energy partition angle. Again, I'll just point out some things for you to save you the work. So Reynolds stress ellipse tilt has a systematic pattern where it grows and decays with the barotropic instability, growing and decaying with distance downstream. The form stress ellipse tilt is messy in the barotropic cases because it's not very important. But in the baroclinic dominated cases, we see a pattern with the tilt increasing, all right, in magnitude while the baroclinic instability is growing. And the eddy energy partition angle increases to a local maximum that happens upstream of the eddy kinetic energy max, which is a useful marker downstream. All of these things show systematic structure in the cross-jet direction. And that's the final point. This is the view for the anisotropy. So it's the same setup. This is the Reynolds stress ellipse and anisotropy on the top and the form stress ellipse anisotropy on the bottom. The long stream evolution of the Reynolds stress ellipse anisotropy shows a self-similar structure across all the runs. I think that's because in the upper layer of these runs, they all have the same barotropic instability because they have the same very narrow jet in the upper layer. So I think that's why that is the case. But we do see important cross-jet differences, especially in the downstream region, depending on the relative importance of baroclinic instability. The form stress ellipse anisotropy shows much more variation. It's much messier, but it does show important variations in depth, which I'm not showing in this view. Okay, key result 3 is that these spatial patterns relate to spatially evolved eddy-mean flow interactions, okay? So here, what I'm showing now, and this is just a test case, this is the barotropic case study. In the black, you see the ellipse anisotropy as a function of a long jet distance. And on the black on this side, you see the tilt as a function of distance along stream. And now I'm comparing it, and the colored lines are the along stream evolution of various eddy-mean flow interaction metrics. Okay, so we can notice that this minimum in anisotropy, all right, aligns where the eddy energy production changes sign. So we go from putting energy into the eddies to taking energy out of the eddies, and that's where that peak occurs. And similarly, you see that pattern in the eddy energy evolution. The Reynolds stress ellipse tilt peaks near where the barotropic instability is stabilized. And so that also kind of makes sense with our understanding, and that lets us know where that maximum occurs. I'll skip. This is a second example for a baroclinic case study. I'll skip it for the sake of time. And I'll go to my fourth final result, which is that the geometric parameter magnitude can vary systematically with metrics of eddy-mean flow interaction. And here I'm showing examples of the dependence of the tilt of the Reynolds stress ellipse, the form stress ellipse, and the eddy energy partition angle as a function of the degree or metrics of the degree of barotropic instability in the top row and of baroclinic instability in the bottom row. And we see lots of systematic patterns with these bulk magnitudes, all right? The average upstream value of the tilt tracks both the degree of barotropic and baroclinic instability in these systems. And I think that's a consequence of how we set up this experiment. The sign of the upstream value of the form stress tilt tells you whether baroclinic instability is active or not. And the eddy energy partition angle varies with the degree of the baroclinic instability of the inflowing jet. So that's my summary. Those are my 4 results I just showed you. I think these results are significant because they suggest how the geometric parameters may vary with varying eddy-mean flow interaction dynamics, how key aspects of the spatial variability in the geometric parameters may be important, maybe need to be incorporated if we implement this as a parameterization. And finally, how knowledge of eddy-mean flow interaction metrics can provide insight into how we should specify the magnitude and spatial structure of some of these terms, or vice versa, if we're using this framework as a diagnostic tool. For our next steps, I'd like to design a parameter study that more cleanly separates the variation of the effects of barotropic versus baroclinic instability. Here we have them both changing at the same time, and I think that is clouding some of our understanding. We can look at geometric parameter variability in more complex and realistic model configurations, and I think it would be fun to test an implementation of the geometric